Our next speaker is Ting-Yu Cheng. Dr. Cheng works as an assistant professor of food animal health, welfare, and production at Michigan State University. His research focuses on strengthening the resilience and sustainability of the global food animal industry from the perspective of efficient diagnosis, early detection, and transmission blocking. So, welcome.
Okay, anyone hear me well? Great, okay, so this is Ting-Yu Cheng, and I'm actually the only one from Michigan on this panel. Maybe that's why Rich called us out by mistake, but yeah, so Dr. French just presented about the experience of using this as a point of care testing at Thailand, specifically for African swine fever. And so we kind of asked another question, what if the African swine fever hit the United States? How would the point of care testing could help us? But fortunately, we don't have African swine fever until today here in the US. So in this presentation, I just wanted to share our experience that using this point of care PCR, the same exactly point of care PCR system here in the US for detecting swine influenza in oral fluid. Yep, so the reason we chose swine influenza is because there is some similarities between influenza and African swine fever. In fact, they both affect pigs of all age groups and impact global swine industry, and they transmit it through respiratory fluids and fomi. So I know it could be a stretch to compare swine influenza and African swine fever, but based on the resources and logistics available to us, mix all of that together. That's the reason we pick swine influenza. So right now we have 4 different types of diagnostics for influenza. So we have virus isolation. It's a gold standard, pretty expensive to run, and it takes a lot of time and only detects viable virus. And now we have PCR. It's very common. I would say it's probably the most method being used for influenza diagnostics. Lateral flow test. This detects the antigen, so it may suffer the antigenic drift, which is pretty known issue for influenza. And the last one we have LAMP, so stands for loop-mediated amplification. So this one's relatively new compared to the previous 3, and it's also PCR-based, so for amplifying the RNA, DNA in the samples. And it could have pretty high sensitivity and specificity if the primary design was done correctly. So right now we have, we look into 2 different systems for this study, and the one just presented by Dr. French, the in-the-field portable PCR system, aka BioMeme. And we had another one, it's called Pocket Nucleic Acid Isothermal PCR. This one's provided by GenReach, and both of them have been validated for influenza detection in laboratory, but the field validation was very limited. So just a quick reminder, this is we call Fit Reassure model. So this is how we evaluate a good point of care diagnostic test. So it stands for, the FIT stands for the fitness of purpose. So a good test should have a good fit of purposes. It should provide real-time connectivity, and the sample collection should be easy either to the producer or to the end users. And the test should be affordable. It should be sensitive and specific, and it should be friendly to the users and provide results rapidly and robust, and should be have minimum requirement in terms of equipment. And the last one is the results should be deliverable to end users. So here, just as presented by Dr. Burritz before, we look into some literatures about point of care analysis, point of care tests we have in the literature. And we found that most of them being proposed have not been validated under the field setting. So in most of the research, they actually develop a pretty good test, and they use it to test to evaluate the analytical performance, and then they move on to test for some numbers of clinical sample, and that's it. They never actually try to implement that in either in the farm, on the farm site, or just any location close to the on the production sites. So for the sample conditions, for this study, we wanted to take a step further and to look into how the sample condition is going to affect the test results. So for example, like, from the farm, producer is going to ship the samples to laboratory, right, for a lab test. And they could take up to 24 hours or even longer. And it could be, sometimes it could be shipped on the ice. And the ice, like, there's so many different conditions. So we look into the literature and we found the influenza infectivity could drop significantly over time under the room temperature, but the RT-PCR detectability should have it should stay the same. So the objectives, we have two objectives. So the first one, again, is to validate the point-of-care PCR test in the field. And the next one is to compare samples tested on a variety of storage and temperature conditions compared to results from official laboratory. So here's how the sample collection was done. So we visited 10 farms from November 1st to December 19, 2023. And we had 4 nursery farms and 6 finishing farms. And we picked 7 pens of the farm for sample collection, for oral fluid collection to be specific. And we implemented fixed spatial sampling. So how that worked is if we got into a barn and we randomly picked the first one, and then the second one is going to be 2 pens down the aisle on the other side of the aisle, and then so on and so forth. So this will ensure the same distance between sample pens. And after that, we hung the ropes. We waited for 20 to 30 minutes, collect the sample. We squeeze the oral fluid out, and then we pour it into a conical tube. So once the oral fluid was collected, we split each sample into 4 sets. So the first set went through a manual RNA extraction protocol on farm. So this one was actually done in an idle vehicle parked right by the barn. So after that, we got the RNA. We split it again to 2 sets. So the first set was loaded into the device and went through the PCR testing right by the barn. And once we're done, we loaded the other set into the device and then started driving from the farm to the diagnostic laboratory. So the second set was tested while the vehicle was moving. And the second set was sent directly to the Animal Disease Diagnostic Laboratory at Ohio Department of Agriculture. And for the third and fourth sets, they went through a 24-hour incubation, either under the room temperature or on ice. And after that, they went through the exactly same manual RNA extraction just in a lab at The Ohio State University. And then they were tested with under the same protocol with the same device in the lab. Okay, so we have 5 treatment groups. For data analysis, we calculated a CT value adjustment. So this one's basically is the threshold minus the raw CT value you got from the samples. And the reason is that because we have a lab result and the result from the point of care system, and they actually have different thresholds. So we use that to ensure the comparability between those 2 systems. And also we assign CT equal to 0 for undetermined samples. And after that, we compare the CT value using Spearman's correlation, and we constructed linear regression models. And for binary comparison, which means the positive and negative, we use logistic regression model. And for specimen sensitivity and specificity estimation, we use Bayesian latent class model. Okay, so first, before we visited the farm, we had 4 out of 10 told us they had either had clinical signs going on or they had a pretty recent outbreak within a month before the sample collection. So the herd vet suspected the herd was infected. And we had 7 samples from the farm tube were not tested for the right group. And the reason is that we did not have enough regions at that time. And there was 1 sample of farm 6. The sample collection was not successful, so it was not tested for all of the groups. And also we found some of the sample, they returned, the internal control was not detected for some of the samples. So we had 15 from the farm group, 20 from the ride, 14 from the room temperature, and 5 from the ice group. So these samples were excluded from the data analysis. And so we found, based on the result from the ADDL, we found 5 out of 10 farm positive and 22 positive samples. So the prevalence was around 31.9. And also, similarly, from all of the treatment groups, they also identified the same 5 positive farms out of 10, except the right, because we missed 1 farm. But for the number of positive samples, there was a little bit off compared to the lab's results. But still, we found, based on the CT value, we found a pretty good correlation between the lab results and the result we got from the point of care PCR among all of the treatments. So the R square is about 90, it's around 90, 85. We have 85, 95, 99, and 96% of the correlation for these 4 treatment groups compared to the lab results. For the binary result, again, it's positive or negative. For this one, we try to control for the number of pigs in the pen, the number of pigs in the farm, and the age of the animals. And we found there was no significant effects of the treatment, which is like the treatment of these 4 groups, affecting the results. And also for the sensitivity and specificity, we found pretty good specificity, all of them above 97%. And compared to the lab test, we found the sensitivity is a little bit lower. We have like 69% for the ice group, 76, 71, 75, so they're all around like 70-something% for sensitivity. So in conclusion, like we found more or less like the result consistent with the diagnostic laboratory, and we found no effect for the sample storage or time conditions. And we found it was, I wouldn't say promising, but it's comparable to the lab results, but still we have some work to do to be able to implement that in the farm. So for the feed reassure model, the fitness of purpose is still question mark, but it provides a real-time connectivity, and it provides the sample collection, which is oral fluid, is very easy for the producers. We're not sure about affordability because the farm producer, or they still need to buy the device and maybe a mini centrifuge. But the sensitivity and specificity is okay, pretty user-friendly, and it's rapid and robust. And it doesn't meet this requirement because producers still require equipments. And deliverability is a question mark because, as Dr. Friend just presented, even though all of the results is uploaded to a cloud, they still need someone to get in there and for result interpretation before it can be understandable for farm producers. And this study bears some limitations. The first is like we have a pretty small sample size. We only have 10 farms, 7 pens out of 10 farms, so 70 samples. And because we have failures in internal control, so we have a pretty limited sample size. And also we only tested in the nursery and finisher farms and only used for oral fluids. So more work needs to be done, in my opinion. And so the future will be, we'll try to investigate the failure in the internal control and to figure out what's the cause for that. And also we will have to test more conditions, like sample conditions and sample types as well. And also we could investigate other point of care PCR-based tests. So just to, first I need to shout out to Everett Delisio. He was the Master of Public Health student, so he was the one making this study happen, and look how much he enjoyed running PCR in the car. And then I appreciate USDA for supporting this project and all of the collaboration we received from the herd vets and the farms, and also Indico for providing technical supports and the devices and region. Any questions?
So what's your best guess or knowledgeable guess about why there's such a difference in sensitivity between the lab and on farm?
Yeah, so my guess would be since we missed like some of the samples based on the internal control failure, so they might be one of the reasons that we see a difference between, because for the lab test, we had like all of the PCR results were valid because they all got, internal control valid. But for our PCR, like point of care PCR testing, there's some of the IC. So we're still we haven't really looked into what's the reason for the internal control failure, but we suspect it could be caused by the on-farm manual extraction protocol. So that protocol was, because we tried to make it work on farm, so we implemented a equipment-free RNA extraction protocol. So it's like a 4x8 cartridge, and each column of the cartridge were preloaded by the region. So you have like lysis buffer, watch buffer, and elution buffer, and also the magnetic beads. But in order to make it equipment-free, we only use a magnetic rod to move the beads between the column and to mix the beads with the region. So that could be the cause of the inconsistency, and that's probably not enough to remove the PCR inhibitors in our fluid.